Welcome, everybody. Good morning, afternoon, depending on where you are in our country. My name is Terry Adamson. I'm the Technical Director with Fenestration Canada. Firstly, this is our Tech Talks sessions, and I'd like to thank our sponsor, Sharif and his team over at Open Janela Software. Appreciate their support of our activities with Tech Talks, so that's great. Today we have the fellows from Red River College. I'd like to thank Alariza Kabarani. Hopefully I got that right. Alariza reached out to me a couple of months ago to tell me that they had completed the research that they were working on for cold climate window installation, and they were eager to share that to the fenestration industry. So kudos to him for reaching out. We really appreciate it when people come to us to share their knowledge and their research results. So that's great. I'd like to thank Hamza Mustafa and Kevin Knight from Red River and other great places, Kevin. So they're going to talk today, and they're going to present on research they did at Red River College on the cold climate window installation. So Hamza is currently working as a research coordinator at the Building Efficiency Technology Access Center, BTAC, at Red River College. Holds a Bachelor of Science degree in physics from the University of Winnipeg. Before joining BTAC, Hamza worked for structural monitoring technology, where he designed and installed sensors, conducting commissioning tests, developed visual applications for data collection. He has extensive experience in using innovative methods to analyze buildings to gain insight into their condition, lifespan, and impact on occupants. Current role of BTAC, he has expanded his knowledge by studying buildings through air tightness testing, thermography, and acoustics, creating mock-ups to be tested in the Center of Applied Research, Sustainable Infrastructure. And Kevin, I don't know if I need to introduce Kevin. I think everybody, certainly in the fenestration world, knows Kevin. Building envelope authority with over 35 years experience in field observation and testing, commissioning, research, education, and training. Kevin's the founding principal of Edifice Tutorial Inc. and was research professional at Red River College, Winnipeg, between the years of 2011 and 2019. Still engaged as a consultant today. 2019, Kevin joined Tower Engineering as their technical leader of the new building science division, instrumental in the development of standards for CSA, including the new coming A440.4. We're holding our breath for that one. ULC and ASTM for building envelope test methods and for commissioning of building envelopes. Welcome, gentlemen. Really happy to have you here. So, Gary just joined us, Gary Proskew. Thanks for joining us, Gary. Appreciate having you here. Gary with Proskew Engineering is mechanical engineer with over 45 years of experience in building science, energy management, research, and training. Happy to have you here. Really appreciate your participation. So, Hamza, if you like, let's get your screen shared and let's walk through your research results. We're bated breath, waiting to hear how it went.
Yeah. See my screen?
Yes.
Awesome. Okay. Hello, everybody. My name's Hamza Mustafa. I'm with BTAC, the Building Efficiency Technology Access Center. So what is BTAC? BTAC, funded through NSERC National Sciences and Engineering Research Council of Canada with the Technology Access Center program, part of Tech Access Canada, not-for-profit organization for expanding TAC outreach. The three main duties of BTAC: applied research, technical services, specialized training and education, and industry private revenue generation. The mission and vision statements. The mission. The Building Efficiency Technology Access Center provides a multidisciplinary environment to facilitate advancements in building energy efficiency and durability while adjusting the building's intended use, its occupants, life service, and climate zone location. Vision. BTAC will establish itself as a center of excellence in building performance, evaluation, and improvement by usage of advanced data acquisition systems, while also following the required government standards, ASTM, ASHRAE, CSA, AMA, BTAC. Profile: serving the building construction industry, owners, operators, design professionals, contractors, building envelope and commissioning agents, products and service providers.
Our main can you step to your next screen? We're only seeing the lead screen.
Can you see this one now?
Your next slide. Yeah, it's not moving.
Oh, really?
Yeah, maybe go into slideshow mode. We're just seeing the the development screen.
Huh. Okay, hold on. I'll end this. See.
Yep.
How about now?
Just waiting for it to come up.
Oh.
Yeah, still, it's not in slideshow mode, but we are seeing the profile
But you're
slide
seeing,
now.
oh, you're just seeing this.
Yes, yeah.
How about now?
No, same thing.
Same thing. That's weird. Huh.
Try the bottom right-hand side.
Got you, English. Oh, hold on. Okay, technical difficulties. Okay, bottom right. Try this one. Slideshow. So yeah, this was strange. I don't know why it's not connecting here. It was just working. Here, hold on. Let me try this. See if this works. Try this. Can you see that now?
There we go. Yep, you bet. That
Yeah.
looks good.
Okay. Can you see the profile?
Yep, looks good.
Yeah. Slides are moving.
Yep.
Awesome. Okay. So BTEC profile, once again, applied research, technical services, special training, mission, the vision. So this is CARSI, the main laboratory, Center for Applied Research and Sustainable Infrastructure. And then we also live in probably one of the best labs in the world in Manitoba with the climate. It's so volatile. Testing equipment are at Red River at CARSI. So the first one is the air-water structural chamber. The air-water structural chamber is used to test durability and windows that will be used in major construction projects. The device is 12 feet tall and wide. The device is sealed airtight through the usage of submarine doors and clamps that keep the wall mock-up tight to the chamber or any type of other mock-up. So what is it used for? Staff or hired contractors build the mock-up walls. The AWS can simulate pressure differentials, wind speeds, and rain amounts that match those of high category hurricanes. The AWS allows contractors to test their walls, windows, before they begin construction, allowing for the highest quality construction designs to be used. The AWS is used for researching new materials and methods for commercial and residential buildings. Environmental chamber. It's two different rooms with a common partition wall. Both chambers can be specific temperatures or humidity. Both chambers are completely airtight when sealed, and we can use another device called a CAN vest to pressure or depressurize different sides of each side of the chamber. Additional equipment that BTAC owns: heat flow meters, air tightness equipment, acoustical equipment, thermal cameras, moisture detection kits, ultrasonic flow meters, and many more sensing. Okay, to get into the research. So cold climate window installation, this is the thermal portion of it, and then we'll get into the water after we go through the thermal. So introduction. The importance of fenestration product installations. The research was conducted. National Research Council of Canada Institutes for Research and Construction has produced significant research led by Lacoste and Armstrong. The research was conducted as extended plot for a 5-year construction technology update that would bring full extent to the laboratory research for industry and focused more on test methods for cold climates, central Canada compared to the rest of Canada, because the difference between BC and Manitoba is quite different for, I would say, below zero. So the testing for us focused on mainly in central Canada. Background: current standards for cold climates fenestration products, Class and Armstrong. So the NRC-IRC had previously engaged in research around climate installation around 2009, 2013. The research raised some serious questions and interesting possibilities that the window industry had unfortunately largely ignored. And in 2013, the research was interrupted prior to completion before detailed review of this research. To inform carefully targeted research, further research could open doors towards more reliable, more efficient, less costly window installations that we see today. So objectives of the thermal portion. Is insulation in the window wall interface necessary for adequate cold climate performance of a window? What is the best location to install the air barrier? Is it possible to adapt the findings to a cost-effective and easily repeatable field installation method? So equipment to be used in the thermal portion. You got the dual environmental chamber. We got the CAN bus blower that will depressurize and pressurize the building. FLIR camera to take any thermal imaging of the fenestration product in situ, and point surface thermistors to measure the temperature gradient across the product. Materials. Materials to build the wall: foam wrap membrane, 3-inch plywood, 2x6 framing at 16-inch off center, 6 mil poly for air vapor barrier, and 1/2-inch drywall. The typical residential construction that we see here in Manitoba. Methodology. So each window, so there's 3 windows, each window went through air leakage testing ASTM E231904. There's 3 different mock-ups. So we have the first window, window 1, without any insulation in the interior stud spaces. The second window with insulation halfway up, with spray foam halfway up the window. And the third window with insulation all the way up, floor to ceiling, and all the way spray foam around the edge of the window. Once installed, each window went through a qualitative air leakage test on the wall. So we determined the air leakage of the actual unit and the air leakage of the actual wall after it's been installed. Okay. Sensor layout. This is a bit overwhelming sometimes to look at, but in simple cases, so we have, try to make it a little bit easier for everybody to look at. On the left side graph, you should see is a blue outline. That is everything interior. So the green, blue, and dark blue, that's on the glass. So those are temperature sensors on the glass. The gray on the left-hand side is on the actual frame inside. And then the yellow, orange to red, if we look at the bottom right-hand corner, they're in this rough opening space. So we have the yellow that's closest to the exterior of the wall, orange in the middle, and the red closest to the interior. So procedure for the testing. So before each unit was installed, well, after each unit was installed, it went through the test, E233104. Test chamber conditions. On one side, the exterior was -30 Celsius, the interior was 21 Celsius with a delta T of 51, and relative humidity stayed at 50%. Once that was done and we had the data for that, we moved on to actually the test configurations for testing the walls. Each wall, so for example, wall 1 went through 2 different tests. So it went through test A with no exterior insulation. So it went -5 exterior, -20 exterior, -30. Then it moved on to test B, where we added exterior insulation to the wall. Run that test again, -5, -20, -30. So there is, yeah. Okay. So here's an example of that test after it's been run. Each test wall is run through for a total of 18 tests. 3 additional tests were run as well for other information that we were trying to gather. Once the average mean state was measured and populated in the graph, the temperatures that you see here is after an hour. So after an hour steady state of everything calming down, we have our temperatures, we have this, okay, we'll start collecting now and we'll end in an hour. And this is the average temperature over that hour. So to dive into the data analysis, because there was over 20 different tests, I'm just going to show examples of 3 to get the point across of what we saw through the data. So first wall, so we got wall 1. If we remember, wall 1 had no interior insulation in the stud space. Okay, so and wall 3 had interior insulation all the way around the window with spray foam in the rough opening. When we compare the temperatures of that, we can see that the temperatures don't change much around the window. The only place that dramatic change is the sill, but other than that, insulation did not improve the window U value, and it didn't decrease it. So there was no real change in that. Kevin, if you have anything different to say about that one.
No, basically there was very little difference in any of the temperatures throughout the whole of the range of the test we ran. So it was nothing significant. Minor changes as the outliers were popular. And so, but basically there was very, very little change in any of the temperatures with any of the setups we tested.
So we got wall 1 compared to wall 3 at -30. So now the next slide is wall 1A at -30, but then wall 1A again at -30, but with a discontinuous air barrier. And with the discontinuous air barrier, we put, let's see if I can mark this up. There is a hole in the discontinuous air barrier, right? Oops. It's supposed to be in the bottom right. So right around here, it's discontinuous. And you can see the temperatures, same wall, same temperatures, interior and exterior. But the only difference is discontinuous air barrier. You can see the air and temperatures move quite a bit through that, getting close to the window.
And that was with a pressurized zone.
That was, yeah, that's pressurized.
So I can't remember what, it was a very low pressure.
I think it was 50.
Yeah, 50 Pascal pressure differential across the chamber. So the moment we introduced flow at the point of the breach in the air barrier, we had significant change in the temperature.
On the next slide, so it's wall 1 again at 30 degrees, at 30, but then wall 1 again at 30 with exterior insulation. So no interior insulation we do with the stud space, but now we have exterior insulation. And you can see how dramatically the temperatures around the entire window changed. The window itself, the glass, maybe 1 or 2 degrees difference from exterior, but around the window changed. So you have a lot more thermal conductivity. Like it's interesting because we see construction here in Manitoba, interior insulation in the stud spaces. But with data, what we see is that on the exterior, it's a lot better. So there's a little bit of confusion there with test standards and industry of how they're building. Conclusion. Is insulation in the window wall interface necessary for adequate cold climate performance of the window? Does the insulation placement in the window installation affect the overall system U value? What is the best location to install an air barrier? So our research showed minor changes in the temperature at the rough opening with window frame and glass. When there is a breach in the drywall or rough opening air barrier, airflow did have a significant impact with a change in temperature. Our research also did not include heat flux flow measurements. So calculating the system U value it needs to be worked on. That's a recommendation we hope to move into the next research phase, is collecting that and building a hot box apparatus for the dual environmental chamber to conduct the U value test, because the window, when tested for U value, does not include the frame edge, and the same for air leakage test. And then for the air barrier location, in line with the glass to reduce, our research saw that in line with the glass to reduce the window frame edge included as part of the air barrier, the nailing frame with the most.
Actually, can I just add a couple of things? Sure. The location of the air barrier is critical, and different in residential standard construction where we're dealing with airtight drywall approach. The more advanced buildings are using vapor permeable membranes over the exterior shielding, the OSB or plywood, in line with the flange window. Every window we used in this, by the way, is a flange window, not a box unit. So it's a standard fixed glazing. And it's a simpler way of wrapping the box is from the outside and trying to get an airtight plane on the inside of the drywall, but that is standard residential construction. So location of the air barrier, in my opinion, is critical on how the whole wall system works, and consideration in their design on what we're doing with open cavity, with drain systems, is dependent on what wall assembly we're using and location of the air barrier. That's also noted in the ASTM 2112, that the location of the air barrier is critical. Also addressing the drainage plane for water and combining the air barrier is beneficial to the wall assembly and insulated outboard again.
Yeah. Terry, should I have any questions for this part, or should I just leave that for the end for the entire? Leave it to the end. Okay.
Yeah, let's leave it to the end. Sure.
Yeah. Okay, so the cold climate window installation for the air water structure. So, introduction. The purpose of phase 2 was to investigate the effects of different fenestration and wall installation methods on the performance of windows in terms of air and moisture movement. Testing focused on residential construction and utilized industry standard materials and wood frame assemblies. Once again, this project is an extension of research conducted by NRC, by Lacasse and Armstrong. Objectives. Can we permanently face sealed out of, can water be permanently face sealed out of wall window interface? How does one component foam perform as a field applied air and water barrier? Are slope sills and back dams necessary to reliably maintain air water vapor barrier continuity? Equipment. So here's our air structured water chamber. So you got the spray rack in the middle, the submarine door on the left, so we can walk in and out if need be. And on the right, you have one of the demos that we have in test wall. I think that was test wall 3. Okay, materials. Air vapor barrier membrane, window shims, accordion style membrane. As people know, there's different types of membranes to wrap. So you got your typical blue skin, an accordion style by 3M, and whatnot, different other styles. Contractor's tape, foam wrap, 6mm polyethylene, insulating spray foam, foam back rod, cement stucco, and steel stud flashing provided by trade installer, and 2x6 spruce wood. Okay. Methodology. Test wall construction, testing schedule, configuration, and data collection. So here's a little example of the construction of the wall. So we would put the window in, either wrap it. I'll get next slide and talk about more how we wrap the rep opening. Window goes in, Tyvek goes on, sensors, stucco, then it gets put into the chamber. And then in the last step, we do the tear test where we test the unit for air leakage on the actual window unit and then the actual buck itself, and then determine the actual leakage of that. Okay. Phase 2. Okay. So testing involved 11 different methods of preparing the ref opening and joining the fenestration unit to the window. So as you see in this table right here, you got window 1 and 2, for example, the ref opening sill. So typically you see like a bid put on the sill when homes or windows are put onto newly fresh homes. So we have a home wrap and then an accordion style wrap, and then the sheathing flange is over. So you have the wrap going over the wrap, only sealing interior. So there's no spray foam or backer rod in the interior. Head flashing, no head flashing, and cladding, none on 1, but on 2, the cladding was stucco. So that changes for each one, where you have different variations for 11 windows. How do we collect the data? So data was collected in 2 ways. One, sensors, and second was visual observations during testing. So notes, pictures, what have you. The sensor layout, we used 8 sensors, put them around the window. Here you can see them installed. And to determine the actual amount of water, because they use electrical resistance for these sensors. Before installing them, we installed a tape just on a table and dropped water on the sensors to kind of, I really relate to the resistance measurement to the amount of water on that tape. The problem that we ran into after the stucco was installed, because stucco holds so much moisture in it, our sensors were triggered most of the time after the stucco. But before the stucco, we could see the water moving around the window. Okay, procedure. For the water test, the window and its buck were tested for any leakage through ASTM E28304. And then to study the effects of different installation methods, we ran the test ASTM E3300. So the one that's a that is a uniform static air pressure and with water on and off for a minimum of 15. We did 5 cycles. So we did water on, off, 5 minutes, on for 5 minutes, off for 1 minute, on for 5 minutes, off. We repeated that for 5 times. The rates, so the pressure that we used for ASTM E331 was 300 for this test. For the tear test, we used 75 pascals. Flow rate, again, was specified by standard. So flow rate was at 3.4 liters per minute. Okay, data analysis. So through data analysis, what we did was we took a graph. The window was, say, soaked. We gave it a scale from 1 to 5, and dry 1, soaked 5. And we went down and looked at 4 areas of the window. So the head, the jambs, sill, and the rough opening in total as being in the interior. So the head, jambs, and sill we wanted to look at on the exterior if water penetrated in the Tyvek, the tape, or anything, the materials holding that window to the wall, to the opaque wall.
Can I just add a couple of quick things here? What we used here really is for a basis is the standard installation that is currently in the field in central Canada. Non-compliant to the National Building Code and the requirements for end damming and flashing. If you want to go back to your setup there, hands up. And we never see end dams on windows, fortunately. And the other thing that's missing in the installation is the requirement for foam rod and caulking between stucco and any fenestration. And in the field and during our consulting services, both Gary and myself have seen a major problem of water infiltration from the head down on the jambs to the corner of the window. Stucco is a great water dam. It holds a lot of moisture in it. So when it rains with cementitious stucco, it dries out fairly quickly, but when we have the combination of acrylics and stucco, cementitious work, just acrylic, the ability to dry outwards is extremely limited. An experience which I had last year was an owner was reporting that he was getting leaks at the head of his window when the sun came up without rain. And as the sun moved around the building, the windows demonstrated the same leaks at the head of the window as the sun moved around again without rain. So what we were having there was an inward vapor drive in through the plywood, into the insulation of the stud wall, condensing on the polyethylene from the air-conditioned space, and then water coming down and dripping onto the head of the window. There was nothing under the window sills at all with this happening, but the actual sill plate of the wood stud wall had basically rotted out. So there's other things going on around the window installation, which is contributing to our building failures in Canada, which has to be taken into consideration as well. So I just wanted to have this audience to understand there's a lot more going on than just the standard concerns with sill leaks. I agree that in weather areas where heavy rain, a weak sill makes regular sense. But in other areas, where still the school is out on what happens with the flux flow sensors on the open sill window. Thanks, Hans.
Thank you. Sensor layout, procedure, exclusion. So after running the 11 different windows, collecting the data here and populating in a graph so we can determine which one was the best outcome of what we saw. So conclusion, it's possible to permanently seal water out of the wall window interface. How effective is field applied one component foam as an air water barrier? Are slope sills and back dams necessary for maintaining air and water vapor barrier continuity? So the first one, can we seal water? When a window is tested for water leakage, the window is face sealed against water leakage and with correct installation of the membrane. A properly sealed, face sealed out of the wall window interface will function. Water leaks will result from either a deficient window fabrication or installation. With the correct design and simple detailing, including effective quality controls in place, can be achieved. The air barrier. One component of foam is not an air barrier as long as is no longer listed in the CAN. I think, Kevin, you can comment on this better than
Yes, it was, I can't remember, it's the UL standard that basically discussed the one part foam as an air barrier at one time. When it was tested as a material, they discovered that the property of the foam is not meeting the requirement of an air barrier. So it's been dropped from the UL standard as just disappeared as a property of air barrier, just taken out. So we can't claim that we're making an air seal using the foam. And as it has very little difference on the insulation value of it, the question is, how important is the foam around the rough opening of the window?
And then are slope sills and back dams necessary for maintaining air and water vapor barrier continuity? For our research, we had trades come in to do the head flashing and help us install windows. I would say the majority of part, every time we asked them to do this, they did not know what it was, especially back dams and end dams for the head flashing. So that kind of just shows the state of industry where we are now, that they weren't aware when we asked them to install this detail, they had no idea. So the 11 walls that we built were omitted from this because this was omitted from the 11 walls because our contractors, traders didn't know how to install.
And it was in the middle of COVID as well. Yeah. So getting people from trades, it was just tough. And we'd actually, at that point, run out of the supplied window samples as well. Mm-hmm. We used them up. So there was a breakdown in communications between the supplier of the windows and the college.
And then after recommendations for further testing, we want to hopefully build a hot box to properly test the U value of the entire window fenestration product on the wall. Have more trades involvement in construction where BTAC or the Red River not involved in construction, but is involved more in the research and data analysis. We would like teams to actually come install, we watch them, move on to the next. And then also various claddings and residential details. Right now, we only see typically one detail in Manitoba, just stucco, your window, maybe a Tyvek bib goes on the sill, and then your window just goes right into the OSB, and then they slap Tyvek onto that. So there might be different variations of cladding or details that could be introduced for research.
And I'll just comment one other thing which we're dealing with in the industry is that when we have a weep sill with a flanged window, ASTM E1105 requires the observation of the leaks. Now, when we have to use the drywall on the inside of the building as the air barrier, what we've done is obscured the ability to observe the leaks possibly from the window. And so at this time, it's very difficult if we do the slope sill, weep sill with airtight drywall on a building. There's very hard, we can't basically test it for confirmation that, number one, if the window's leaking, it's kind of like, well, it can leak now, but it's the rough opening and the preparation of that will be leaking into the opaque wall system, which is a high concern. And the degree of difficulty of getting a complete air and watertight seal pan installation with membranes, with weather-resistant barriers, very difficult, if not impossible. Using the membranes is difficult, and human error is very high in that kind of installation. So the ability of doing quality control work is hindered by the air barrier being the drywall and the flange in the window obscuring the visual reference for the test.
Thank you. Yeah, questions?
Okay, no, that's great. Anybody online have questions? John Eakes? John, can we hang on a second here? Let me just find this. Okay, go ahead.
Mute. Does that work?
Yep, I can
Can
hear
you
you.
hear me? Okay.
Yep.
Okay, I'm looking particularly at the thermal part of the report, and I'm interested to see that you did show that insulation has a less effect on the overall performance than we seem to assume, thinking that we have to insulate everything all over the place. I didn't understand why you chose to insulate the bottom half of the window coming up the sides and across the bottom. When I initiated this whole project 4 years ago at BTAC, we were talking about pressure equalization and drainage planes and wanted to know if we could have our insulation on the inner side of the wall, but not going so far out to fill it all to leave room for a drainage plane. That apparently has gotten dropped totally from your research. So the whole thing now is also, I'm a little bothered by all the moisture part that you go that is in total contrast to the research you cited from the National Research Council at the beginning, where they found that the face seal approach didn't last in the long term, and they were looking for other ways of controlling things. And when I first initiated this project, it was how do we bring the pressure equalization that's used thoroughly in commercial installations, window installations, how do we bring it into the residential field? And we're hoping to see more details on that. But what you've done does show us a lot, but doesn't seem to really prove that any of those methods are working any better than just what we're doing today. I don't understand why you chose to insulate the sill and up the two sides and not insulate the top half. It was like maybe we lost the message at the beginning when I said insulate half the interface. For me, it was from the inside of the house out up to the glazing point, stop there, and then let the moisture have a control mechanism on the outer portion. But your research report doesn't even seem to touch that. Am I missing something here?
Oh yeah, basically the 3 different layers of insulation in the cavity wall was just to see if the infield insulation has any impact upon the window. So we have a comparison from the sill or halfway up to the head, and we didn't see any temperature change in those 3 different conditions. So that was just like the baseline to do it. Now, the pressure equalization is a complex thing to actually discuss here. What we need to have pressure equalization is a compartment that is vented so that the pressure from the outside of the wind to the inside of the cavity is pressure equalized to stop wind-driven rain into that. Now, when we look at how we actually have the cladding coming into place with this, to actually then think we're going to weep around the opening of the window and get true pressure equalization, that is a very hard question. I think what you should be focusing on is really it's just a drain screen, not pressure equalization. It's literally not functional for trying to create pressure equalization around the fenestration of the window.
In the George Brown College study, we demonstrated that it works.
But that was not pressure equalization, that was a flow. You didn't have
No. The plug was to make an airtight barrier on the inside. The wind-driven rain on the outside with access to the sill area that came up the two sides was a standard pressurization mechanism, and we could visually see it stopped the driving force of the rain across that outside membrane.
But you should have had a pressure tap from the outside to the inside to make the statement that it's pressure equalized. That wasn't proven.
No, it was true. We didn't have measurements, but we did have visual contact that the water quit coming. as soon as we opened up the pressurization, or at least when we sealed the air barrier. So, I mean, there are a lot of things that we can criticize about George Brown College because it was a very small study in a very restrained space. But I was on yours, I was hoping to see much more along this line with your much more sophisticated installation. But I see that you chose to go elsewhere.
No, because the term of pressure equalization, we would have to then, if we consider that, you have to take the pressure taps across the zone of the inside of the window opening to the exterior wall. And it's the response time. So you get P1, P2, so you end up with P1, P1 response time to make any claim on pressure equalization. And that wasn't done.
That wasn't done. Yet we have visual claim that we can see the water was pissing across when there was a poor air barrier, blocked the air barrier, the water just dripped down and dripped out.
So therefore, sir, you were saying that basically you have a drain screen that's effective, but not pressure equalization.
Well, we can't guarantee the pressure equalization except that it had an effect there. The fact that when we stopped the air from blowing through, obviously pressurized that cavity. And, you know, there's much more research needs to be done. But what we did show is we could control the moisture without any sealing on the outside. You seem to be just looking for ways to better face seal after the National Research Council spent 5 years indicating that that doesn't work in the long term.
Face seal is just one hypothesis. Same with the rain screen and pressurization equalization. They're all hypotheses. They're still being tested and they're still being figured out. They're still not to the stand. Like they're not there yet. So we were
different designers using different boundary layers of material that has to be considered in all window installations where your boundary layers for the building envelope are connected to the window. We can't just say this is good for all. It's not one size fits all. Yeah, we could talk for this. We could have a separate conference on this, but I think we should give other people time for them.
Yes, absolutely, absolutely.
Ask a question. Thanks.
Agreed. I was a little bit confused by wall 2 as well, with the insulation running halfway up. What was the result, and what you believe to be correct is that the insulation in the rough opening cavity had little to no impact on the edge performance of that window thermally? Is that what I took from that?
Correct.
Okay, great. That's good. Question from Cliff. So he's asking, out of this, what's the optimal barrier system configuration?
That's a whole conference, but I like the universal wall system. I like to make everything simple. So in the design, I like to define what the actual barriers are and what the materials are. Then I want to align the barriers within the wall assembly to make it as simple, straight line as possible. So when we think about thermal barriers, doesn't seem to be impacting on the window as much as the opaque wall assembly is so important. Putting extra insulation for making the opaque wall system very effective on the outside doesn't seem to impact upon the window's performance. But then when we come down to the air barrier and vapor barrier and drainage plane, we can get that in one simple material if we heavily insulate outside of that. So air, vapor barrier, drainage plane, insulate outboard, all potential wetting then is outside of the drainage plane. That's the universal wall preached by over the past 30 years by many people, but we don't build houses like that. We build commercial buildings like it. So technically, when we think about where the dew point is in our residential construction, it's always going to be inside the stud wall. And then we have to have a very, very effective water barrier on the exterior plane. We're using materials that hold water for prolonged periods of time, allow for inward vapor drive, and with low ability to dry. So the answer, sir, I think is basically, yes, keep it simple, insulate outside of the wood frame, but you have to change the mindset of the strip builders. And Hans and myself were just talking earlier about the people who are buying these 600, 700,000 homes with like bad building science practice. So I feel sorry for these people. So the best wall is keep it simple, align everything, straight lines, and define your functional layers.
Okay. Cliff has another, this is more of a comment with a bit of a question at the end. And I've never seen this detail, so I find this really interesting. He says, During the Green On installation training, we were instructed to have 2 independent beads of insulating foam, one on the exterior and one towards the interior with an air gap in between. Have you tested this?
Good luck in storing that one.
Yeah.
Ever try to control urethane foam? That makes
Yes.
no sense to me. Sorry.
I've never
if
seen
you're
that.
going to use foam, in my opinion, if you're using foam, it should not be inborne of the glass line, because then you're trying to keep the inside temperature to the glass edge warmer. If you start foaming beyond then you can reduce actually the temperature. Maybe you get some condensation points there. So if I use foam, I always try to get it outborne of the glass.
Okay. Adam says the best practice I've seen in the industry is for an exterior air barrier protected by thermal insulation and exterior rain screen facade. The best thermal for the window is for the thermal layer to return into the window RO to protect 3D heat flow. Do you agree to that?
Absolutely.
Yeah.
Okay. Whoops, hang on a sec here. I've got a hand up. Bear with me as I work my way through it. George Torek, go ahead.
Yeah, one thing to keep in mind that notion, the detail for 2 beads of foam, it's not related to pressure equalization at all. That goes back to the days, particularly the 1980s, when foams were being used to insulate the rough opening gap, and they were very high expansion. So the idea behind 2 beads of foam is that you lay down 1 bead of foam and you let it expand, and you lay down a second bead of foam, and the space between the 2 beads of foam provides for expansion, because the foams typically used for installation are one component moisture cure, and they can take many hours to fully expand. So if you fill the rough opening gap with foam, at the time in the 1980s, these were very high expansion foams. They could buckle the frame. So the idea of the gap between the 2 beads of foam was to allow the foam room to expand within the rough opening gap without putting pressure on the frame. Now, we still include that within the A440.4 standard, because and it's the discussions that we've had for the current edition, that even though the industry has now developed softer foams, the window and door foams, that generally, in theory, don't have that power to expand so much that they can cause buckling. The reality is we are still seeing that happening, because now people are going in and just blowing the whole cavity full of foam, and they figure it's window and door foam, no sweat, won't cause a problem, but it can buckle the frame. So we keep that in there, not as a pressure equalization tool, but to make sure that if foam is used, that it's not going to buckle the frame.
Yes, indeed. Thanks, George.
Thanks, George.
Just a comment from Corey about the availability of this session. All of our sessions are recorded. All the Tech Talk sessions are recorded and available on our website, as well as on the Fenestration Canada YouTube channel within a couple of days of the event. So just keep an eye out for that. I thought I saw another hand, but maybe it disappeared. I don't see it. Is there a final report to this research that we would be able to have access to, or
Yeah,
no?
we do have a full report, a written report, and I believe Ali can chime in on this as well if he needs, but I believe we can send it out to Fenestration Canada. I'm not sure who of our industry partners will get it first, and then I think Fen Canada will get it after industry partners. I believe, but Ali can correct me if I'm wrong there.
Okay, great. Okay, so help me understand the water air testing. Was that done just with a face seal installation detail, or was it done, like I'm on the West Coast, and most of what we see today is a rod and caulk detail tied into the environmental barriers at the back of the window. So I'm just wondering what the actual detail of installation was for the air and water testing.
Yeah, we did both on the thermal with the gap, but on the water, it was just a face sealed one without the gap. So we had, I think, a 1/4 inch gap on the thermal with the standoff from the flange to the wall.
Yeah.
But on the Other two, we just had, again, that the trades just didn't understand even how they would work with a weave sill, with the ones who came in to install the stucco. And we were pushing hard, trying to find the trades at the time was literally impossible. And I say that was in the middle of COVID, so no excuses, but no, we didn't do a weave sill on the water.
More testing needed. Okay, Murray, go ahead.
Can you hear me okay there? We're on the middle of a construction site in nowhere here.
You're good. Yeah, you bet.
Okay. I just, you know, I got a million comments here, but I want to remain constructive. But the question that I have is, you know, Part 9 has some limit states on there that I think are potentially being ignored from what I just saw here. And that is that you must have a first and second plane of protection. Whether or not you got a capillary break, you need both. And the second plane of protection prescriptively must be continuous at all penetrations. And it goes on further to say, including at windows and doors. And because you can't guarantee that a window frame might not leak or might not develop a leak, it's a pretty clear understanding in all of our assignments that you got to have that second plane of protection, returning in the rough openings and be continuous to the innermost line of the frame. And what I'm seeing in these details in these conversations here is, you know, I feel like I'm in the 90s here. We talked about all this. We've tested this to death in the West, and it doesn't work unless that is the detail that we adhere to. And the second point is none of the spray foams that we have reviewed in the market have any information or testing for their thermal property. They're not insulation, they're air sealing foams. So, you know, and I'm not surprised by the results here, because if you look at the window and you look at the performance of the rough opening and compare that to the airspace and the surface films, the rough opening empty is not the weak link. It's the frame on one side until you get to extremely high performance windows, or the 2x6 itself on the other side built up as at least a double lamination. So insulating, not the weak point, not surprisingly, doesn't nudge the numbers very much. So I thought we'd already answered all this stuff, and I'm confused by why it is we tested what we did here.
We used what we commonly see for the water test in the field. It's not code compliant. I agree with you, sir, absolutely. But the first two ones we wanted to do was to set the base standard of what the current practice was in central Canada. And again, the next step of that wasn't available to do through conditions with the trades and with the COVID in the middle of it. So those next step to put the head flashing in, the caulking in, and then finally would be a weave sill. Unfortunately, that wasn't done.
So round two of the testing. Go ahead, Murray.
Yeah, no, yeah, maybe, you know, I'd love to see additional input in the methodology, so that we're not spinning our wheels doing stuff that's been done 1,000 times already, and actually be moving forward on what our understanding is.
I agree, but there's also like when you go around, even if we introduce new details, new methods, new hypotheses, they can't do it still. So we're going to keep introducing stuff that people can't do right now. Like they can't build right? You know what I mean?
You know, the problem is what they're doing right now doesn't work, so you can't afford to let that happen either.
Yeah.
Like, you know, this,
yeah, I totally agree with you.
But we can't get them to be compliant with current code without introducing anything else. Another degree of difficulty is just going to be ignored in the field. Mm-hmm. Unless we're
I'll leave you one thought. We're all going to a tier code, and we're all going to net zero for all new construction by 2030 by law in all of Canada. It changes the complete assembly, the nature of the windows that are going in. So we all have to relearn what we're doing to satisfy that requirement that in the builder's world is only 5 years down the road. That's when design will have to be at true net zero. So what it means is everybody has to be retrained. I would hate to think that we would hang on to something that might sneak you through to tier 2 or tier 3 when it's going to be throwaway before it even comes into place. Like, we know how to train at true net zero, and we know how to achieve tremendous success and satisfy the current language in the code, which I contribute to regularly on the joint task groups, etc. So yeah.
And following all those standards and everything, going through commercial buildings, they work great. Everything's going. But for residential homes that we see, nothing's working for that. So like net zero for a residential home in central Canada, they can't achieve it because the building isn't there yet. but for commercial buildings, it's working, right? So
And when we talk about the different designs, we had definitely have the drained wall system with the standard flange, air barrier, drainage plane connection, defining the inside of the building and the outside of the building. We still maintain that secondary drainage plane.
Yeah, but if you take a look at second plane of protection, they do define that separation point.
Yep.
And in part 9, it's very clear it has to be at the innermost point, because you got to ostensibly prevent rain or snow from going any further, and you must provide for dissipation of that intruding moisture back to the exterior. So you either got to have a drying assembly to the outside, a draining assembly, or a combination of the two. You slap a sealant around a nailing flange at the face of that, and any failure in that window frame is now completely a patent defect in code under part 9. So what I'm saying is, I get that there's a lot of people building stuff out there that is just stop the sheathing, glue a nailing flange in, and away you go. Put a little crinkle Tyvek on there and hope that that acts as drainage. But the simple truth is, it doesn't make code currently. So what's going on there in testing? What doesn't make code? And I'm a Supreme Court expert in BC and in the national, and this is exactly the way the courts interpret this stuff.
Lots of work there. Okay, we need to carry on. We're just about out of time. I got Nick that says, is there any comment on the thermal merits of cutting the building wrap at the exterior window opening and sealing the flange to the OSB directly versus wrapping the barrier into the window opening? Anybody want to jump on that?
So yeah, what we saw was the window did not perform very well when it was just on the wood OSB. But when you did wrap a material, mostly membranes, they did outperform a home wrap. So if you did wrap the home wrap into the rough opening, okay, it did help the window a little bit more than the wood. But if you put a membrane type, more like a blue skin almost, that helped it a lot more substantially than wrapping Tyvek. Yeah.
Okay. Murray, go ahead.
I'm sorry to do it, but you can't use a vapor tight membrane to the exterior of the insulated wall.
I agree 100%. That's why we have vapor.
So one place when we did the survey of building envelope failures in the coastal climate of BC, which was the basis paper at the beginning of the whole nightmare at the late 80s and early 90s from leaky condo, the one very distinct observation that Ricketts et al. Came to in that, and it was based on all of my files of literature, the only place we could find evidence of construction-related moisture failure or damage was at window and door openings where they were wrapped continuously with vapor-tight membranes, specifically blue skin. It's because the construction moisture...
I agree 100%. That's why we use vapor permeable membranes.
Right, but we've been able to detail Tyvek and make it work easily, as well as it's just completely different skill sets. And you still has to be a waterproof membrane because you're not allowed by any of those product manufacturers to lay anything off vertical. If it's a sheathing membrane or a vapor permeable, they don't warranty it if you use it as a roofing membrane, so off vertical. So they use the mansard as the division slope between a roof and a wall. So and that's defined in the code. So we do use waterproof vapor tight at the sills, but that's the only location, and only 8 inches up.
Yeah, but there's multiples of materials now on the marketplace that have high vapor permeability that are a membrane and not defined as a weather-resistant barrier. They're an air barrier, vapor permeable, water barrier, which gives you a well-defined control of your properties of your building envelope.
Yeah, but when we stand water on there without minimum slope, it gives out.
Which material?
And all of them, VP 100, stick VP, you name it, like all of them. That's just what we do every single day is we buy stuff, get stuff, test stuff, and we figure out what works and what doesn't. And those membranes, they start to lose their adhesion at their joints. It puts too much pressure on their primers. And if you got back dams in there, we start getting really negative things happening at that location too. It's pretty tenacious. But yeah, it's also a matter of the material manufacturer's warranties, right?
Yes. And
they'll run from it.
What about the liquid applied air barrier vapor permeable?
I love liquid apply, but there's no provision in Part 9 to use the liquid apply. So you're triggering an alternative solution, which is either an engineer or recognized expert, to be allowed to use it. And then there's a field quality assurance protocol that goes with it. I don't deny it. And I don't know quite why at this point we haven't come around with the beautiful liquid applies that we have out there. But unfortunately, under Part 9, we can't find a way to argue it as a Part 9 solution. We're trying to stay away from all engineering all the time.
Okay, I want to respect everybody's time. We're actually out of time, running over a little bit. Just a couple of comments from participants that I want to bring in. So Ron says 2 beads of foam leaves 2 uncut skins on the foam beads towards the center of the window, where the interior exterior faces may be trimmed if over foamed, which otherwise can defeat air seal properties. Fair enough, just a comment. And then Adam says vapor permeable cannot be used as a sill pan. And I think that's what that discussion just went through. So again, we're over time, so I want to respect everybody's time. I want to thank Kevin and Hamza for participating and bringing this to us. We look forward to the final report and seeing what that looks like. It sounds like there's a whole lot of research that is still needing to be done, and we're certainly hoping that we can partner and work with you guys on that. I do want to just do a couple of plugs for some Fenestration Canada activities. The Canadian Glazing Conference is coming up at the Civic Hotel in Surrey on April 9th. Civic chapter at West Tech Windows, April 11th. The Atlantic chapter at the Mapleton Lodge, April 24th. Ontario chapter at Graph Industries on May 1st. The Quebec chapter at Robivert on May 9th. Top Glass is being held in Toronto on April 29th. The FenCan AGM conference in Kananaskis, Alberta, May 28th. Go to the Fenestration Canada events tab for all of that activity. Gentlemen, I want to thank you so much for joining me today. And yeah, sounds like there's a whole lot more work to do. So appreciate your time.
Thank you.
Thanks.
Thanks, guys.